Today, we want to start with the geometric interpretation of complex multiplication. And to tell you the truth, the geometric interpretation of complex multiplication is the key thing that makes complex analysis go, you might say. Okay, it's like a literal key you're sticking. Okay, you never stick keys into cars anymore. Okay, old cars. Stick the key into the old car, turn the ignition. It's what makes complex analysis go, the geometric interpretation of complex multiplication. So let's talk about that first with an example. I'm not going to do general proofs. We'll just consider examples and make graphs in Mathematica to illustrate things. The letter Z is a common letter used for complex numbers. I will go with the standard letter here. Z1, say, is 4 plus 3i, and Z2 is 5 plus 12i, where, as always, I is the imaginary unit defined to be the number whose square is -1. And people argue and say, well, there is no such number. And we argue back and say, yes, there is. There's no such real number in the ordinary real number system, but we can create new numbers, imaginary numbers that are multiples of I, that has this property, and complex numbers that are of the form some real number plus another real number times I. The first real number not next to the I is called the real part. The other real number next to the I is called the imaginary part, even though it's a real number. Keep that in mind. It's just next to the I. To create a complex number, and we can define a consistent kind of arithmetic. The only kinds of questions are, is it interesting? Is it beautiful? Is it useful? Are the main questions that are unanswered at this moment. Let's remind ourselves how to compute the product, Z1 times Z2. That would be 4 plus 3i times 5 plus 12i. We FOIL as if these were two polynomials in I, but then we use the fact that I squared is -1 to simplify. Whereas you don't do that with polynomials, right? You don't assume x squared equals -1 with a polynomial. But FOIL, first times first is 4 times 5 is 20. Outside times outside is 4 plus 12i is 48i. Inside times inside is 3i times 5 is plus 15i. And last times last is 3i times 12i is plus 36i squared. But then you jump for joy. This is the joy of complex arithmetic and ultimately complex analysis. You replace I with -1, which means ultimately plus 36i squared gets replaced with -36. Group together the real parts. 20 minus 36 is -16. Group together the imaginary parts. Add like terms if you like. 48i plus 15i is 63i. And that evidently is the product of Z1 and Z2. We will check our answers and make interesting graphs with Mathematica, though other programs are available too. In Mathematica, capital I is the imaginary unit. So for example, if I square it, I do get -1. Okay. I can plug in Z1 and Z2 in here. Notice the capital I is being used. Then I can compute Z1 times Z2 and confirm the answer is -16 plus 63i. So this is how you do it algebraically, arithmetically. What's the geometric interpretation of complex multiplication? Right, so I'm going to make a picture over here of a plane, a complex plane. What makes this a complex plane? It's all in your imagination, puns intended today. Okay, in your imagination, you label this axis the real axis and you pretend it is the real number line. You think of it that way. You label this axis with the word imaginary, but it's there. Yes, it's in your imagination, but I drew it, right? Okay. I mean, all perception, in a sense, is in your head, right? It's in your brain, it's in your imagination. Still ends up being useful. How do you graph these things? Z1 is 4 plus 3i. Let's pretend 4 is right there and 3i is right here. I could label that with just a 3 and just remember that it's along the imaginary axis. But it also does happen to be where you would plot the complex number 3i. 0 plus 3i would be that point on the imaginary axis. But we're after this point, 4 plus 3i, it would be right there. There's z1 equals 4 plus 3i. Where is z2? 5 plus 12i. 5 is, say, right about there. 12i, maybe right about here. So I would be at this point, z2, 5 plus 12i. And then their product, negative 16 plus 63i, well, that's, maybe it's negative 16 is over right around here, negative 16. And 63, that's way up here, maybe even above the word imaginary there. But I will draw it to be like here, say, 63i. So we're up here approximately, okay? So there are dots, points, representing these 3 different complex numbers, z1, z2, and the product, z1 times z2. From this picture as it is, there doesn't necessarily immediately jump out at you a way to geometrically interpret this until you start maybe making some conjectures and trying some things. Like, you say, well, these are points, but I could also think of them as vectors. I could draw arrows to these points and think of the complex numbers as being vectors if I like. That's a possible thing I could do. And if you stare at it long enough, you might wonder, I wouldn't add these 2 lengths to get that length, but I wonder if I multiplied them. If I multiplied the lengths of these 2 vectors, would I get the length of that vector? That could be a conjecture you'd make. And then you could check and see if the conjecture works. Let's go ahead and do that. What is the length of the first vector to z1? A natural kind of notation for that is the absolute value of z1. And you can say absolute value if you like, though it's more traditional to use a different word here. The official word is modulus. This is the modulus of z1. It has nothing to do with modular arithmetic, if you know about that, but it is a similar kind of word. Modulus of z1. And how do you figure it out? You choose Pythagorean theorem. There are, right triangles you can draw, like this one here, and use the Pythagorean theorem. Though if you do that, keep in mind, you're ultimately going to be doing a square root, not of 4 squared plus 3i squared, but 4 squared plus 3 squared. You're kind of ignoring the I when you do this, because it's just an ordinary application of the Pythagorean theorem to an ordinary triangle that I've drawn, an ordinary right triangle. So don't make the mistake of thinking you need to square 3i there. 3i squared would be -9, and you'd have 4 minus 9, -5, and the square root of -5. That would involve the imaginary numbers as well, but we don't want to do that. We want the distance to the origin, the length of that vector, to be a real number, a positive real number, in fact. And I've made the numbers work out nicely. That's square root of 25, which is 5. Similarly, I can compute the modulus of z2. z2 is 5 plus 12i. I could draw a right triangle again over here. Try to figure out the hypotenuse length there. And I get square root of 5 squared plus 12 squared. Square root of 25 plus 144 is square root of 169, which is a nice number, 13. How about the modulus of their product? z1 times z2, what is their product? It's right there. So I do square root of -16 squared, which of course is the same as positive 16 squared, plus 63 squared. It's not clear that this will necessarily be a nice number. 16 squared 256 plus 63 squared. Ultimately, I'm taking the square root of 4,225. Is that a nice perfect square? What is its square root? Yes, a nice number, 65. This is 65, and lo and behold, 65 is 5 times 13. So yes, I did, for this example at least, see that the modulus of the product, Z1 times Z2, is the product of the moduli. Fun to say. The modulus of the product, its distance to the origin, which is the same as the length of the vector out to it, is the product of the moduli of each individual factor. This is just like polar coordinates. This is like the r coordinate. And with complex numbers, you multiply the r coordinate of the two factors to get the r coordinate of the product. That should seem kind of cool. Is it true in general? We're just verifying it for one example. But yes, it is true in general. In general, though it takes proof, the modulus of Z1 times Z2 is the product of the moduli of Z1 and Z2 individually. That is true in general. But is that all there is to say? That's in, like in the polar coordinates, the r coordinate. What about the angle, theta coordinate? Are they related? Yes, they are. And also in a simple way, maybe you would conjecture if you might conjecture multiplying the theta coordinates, but that would be wrong. You actually add the theta coordinates. I'm multiplying the complex numbers, but I add their angles. Let's see if that works with this example. Another funny name in complex analysis, excuse me, the angle is called the argument. Arg Z1, that's the argument of Z1, is the polar coordinate angle. I could label it theta 1, but I'll stay traditional with complex analysis here and call it the argument. Though, as with polar coordinates, it's not unique. If you're in radians, you got an argument, you can add any integer multiple of 2 pi to that and get the same, another representation for the same angle. Another argument for the complex numbers. So you do add the angles with the caveat of how to interpret that to get a new angle for the product that is one of many, infinitely many angles for that product. How do you figure it out? Again, use trigonometry. Let me redraw, say, the smallest triangle here. Smallest right triangle. In that picture, this side had length 4, this side had length 3, this side had length 5, the hypotenuse. The argument is the angle there. I could use an inverse trig function. I could use inverse cosine or inverse sine or inverse tangent. I could, thinking of cosine is adjacent of our hypotenuse. I could do the inverse cosine of 4/5, 0.8, or the inverse sine of 3/5, 0.6. Or the inverse tangent, that's what's most typically done, of 3/4, and get the same answer. Keeping in mind that inverse tangent and inverse sine always give you an angle that's between negative pi over 2 radians and positive pi over 2 radians, an angle in the first or fourth quadrant, not in the second or third. So if your point, like the product Z1 times Z2, is in, say, the second quadrant, that's not going to be right for that point. I'd have to add pi radians to it, for example, to get the right angle. But this will work for the first angle. And just to keep the interpretation simpler, if you use your calculator with me here, go to your mode and make sure you're in degree mode instead of radian mode. You know, we use radians 99% of the time in calculus because, maybe you don't know this, but because it makes calculus simpler. The derivative of sine of x is cosine of x, as long as x is in radians. I don't know if you know that. But if the input for sine is measured in degrees, that's not true. The derivative is not cosine. It's some multiple of cosine. Okay, the radian measure makes a difference. Anyway, I'm going to go to degree mode because it'll just be easier to visualize. Inverse tangent of 3/4 in degrees is about 36.87 degrees. 36.87 degrees. And yeah, I could have used inverse cosine of 0.8, same answer, or inverse sine of 0.6 is the same answer. Actually, if your angle's in the second quadrant, you could use inverse cosine for that kind of angle, because inverse cosine gives you an output between 0 and pi, first or second quadrant. All right, what about the argument of Z2? Arg of Z2. Inverse tangent of what? I could draw a triangle again, but just do it in your head here. It'd be inverse tangent of 12/5. Take the imaginary part and divide by the real part is what we're doing here. With Z1, there's 3/4. With Z2, it would be 12/5. Inverse tangent of 12/5. 12/5 is 2.4. So inverse tangent of 2.4 is about 67.38 degrees. 67.38 degrees. What is the argument or an argument of their product? The product is over in the second quadrant. It was the -16 plus 63i. If I do inverse tangent of 63 divided by -16, I get an answer in the fourth quadrant. To get the right answer, one allowed angle for this, I need to add pi radians to it, or since I'm doing degrees, I'll write it as 180 degrees. Inverse tangent of -63 over 16. The 63 comes from the imaginary part, the 63i, and the -16 comes from the real part. I put the negative sign in front of the top here in the calculator, it doesn't matter. Plus 180. When I enter this, I should get the sum of these two, which is going to be what? Do that in my head. 104 something. Yep, 104.25. Those rounded pretty closely. I think if I take 36.87 plus 67.38, I do get 104.25. Yes. About 104.25 degrees. Make sure you use the degree symbol when you are using degrees, or else the word degrees, or DEG. It is true that in general, the argument, or an argument of the product, I should say, can be found by taking an argument of the first factor plus an argument of the second factor. You got any two arguments, any two valid angles for Z1 and Z2, you get a valid angle for the product, Z1 times Z2. This equation is a little funny in how you interpret it, but that's what I said verbally is basically how to interpret it. So when you multiply two complex numbers, here's the key. I'm not going to write this down. I'm just going to say it for sake of time. But this is the key that makes complex analysis work. You multiply their moduli, their distances to the origin, length of those vectors, and you add their arguments. Add the angles they make with the positive real axis. That is the key that makes complex analysis go. It's the key for all the significant things in complex analysis.